Hello and welcome to the Erlang Solutions monthly webinar. My name is Mladen Miličić and I'm the Solutions Director here at Erlang Solutions. Today's webinar represents a continuation of a series of webinars we have been running across topics of interest in the world of Erlang and dealing with solutions based on the Erlang programming language. Today we will talk about the Leapsight Semantic Dataspace, and this next generation database offers a bleeding edge approach to marketing concepts, tools and campaigns that are truly tailored to each individual in audiences that can often number millions. And all of this will be based and is based on an Erlang framework offering the massive scalability and the extreme fault tolerance and concurrency needed to deliver such performance. As with any live event, please excuse any technical issues that we may encounter today. Now, to start by telling you a bit about Erlang Solutions, we are a products and services orientated company completely devoted to the Erlang programming language. Since our founding in 1998, we have worked with organizations and individuals using Erlang, helping evolve the language and supporting people and businesses using it. Today we have about 80 people across our offices in London, Stockholm, Krakow, Budapest and most recently Seattle, and working on projects across the globe. We are very keen on creating value and competitive advantage for our customers across industries and through the unique features and characteristics of Erlang as a programming language. As you might guess, we are ambitious in development of Erlang-based products, and we work to create lasting partnerships with our clients. The products and solutions we market include Mongoose IM, which is a massively scalable messaging platform, the React distributed data store, and other solutions applicable across sectors and problem areas where Erlang as a language makes sense. I am particularly pleased to say our speaker today is Alejandro Ramallo, the co-founder and CEO of Leapsight and the creator of Leapsight Semantic Dataspace. Prior to Leapsight, Alejandro was the Chief Technical Officer at British American Tobacco and then chose to pursue his ambition of delivering the next generation Erlang-based data store as foundation of individually tailored marketing efforts. Please allow me to finish by saying you are welcome to post questions throughout the duration of the webinar by using the chat facility. Our speaker, Alejandro, will answer as many questions as time allows at the end of the webinar. If any questions do go unanswered, you are welcome to raise them via email using the following address, that's webinar@erlang-solutions.com. If you're interested in learning more about Leapsight Semantic Dataspace or Erlang, or just wish to establish whether they could be a solution for the challenges your own business may be facing, then by all means, please feel free to contact myself directly. My email address will be displayed in one of the final slides of the presentation we will share with you. The same goes for any other questions you may have. Feel free to contact us. I would now like to hand over to Alejandro Ramallo, who will be glad to start us off.
Hi, hello everybody. Thank you very much. First of all, Mladen and the whole Erlang Solutions team for having me here, inviting me, and thank you all guys for and girls for being here. So we're going to try and rush through the first number of slides. We don't want to speak a lot about who we are, but just a brief as a context to let you know why are we doing what we're doing. Then go through the challenges that we faced in the last 10 to 15 years as a team developing front office solutions for consumer goods, and how we decided to take on those challenges in terms of developing some technologies that we're now presenting. So a little bit more about myself. As Mladen said, I had in the last 10 years I spent most of my time working for British American Tobacco. Before that, I worked for other consumer goods companies as well. I've been architecting marketing technology solutions since '97. We specialize as a team as well as in consumer engagement, trade marketing, sales, and distribution. From a technical point of view, we arrived at Erlang early in 2010, I would say. Before that, we were pretty much concentrated on object-oriented technologies. I've been doing object orientation since the days of OpenStep with Web Objects and the Next Step platform. So who we are? So we define ourselves as architects of new solutions and technologies to help you dig more accurately and more deeply into consumers' world to engage and create and nurture long-lasting relationship with your brands. And we're going to expand into this topic and understand how this differs from the typical CRM processes that you might know. And enough to say about Leapsight that we started operations in 2011 here in the UK and in Argentina. We have a strong background in architecture and implementation of bespoke, scalable, high availability solutions for marketing. And we typically engage with customers doing, from strategy and architecture consulting all the way down to developing this platform. In particular, through our last 10 to 15 years in British American Tobacco, we envisioned and designed and implemented a platform that has no equal in the consumer goods environment. So basically, since 2001, we've been engaging consumers on one-to-one basis and tailoring the offers to those consumers in real time through multiple touch points. That is branded websites, interactive kiosks, integration with postal services and SMS and email. The other consumer goods companies are still not jumping into these, and basically we needed to go into this environment because we were losing all communication channels with consumers due to advertising restrictions. And therefore we decided to go and implement this one-to-one solution. Now, by the time we did these, obviously we started using the tools that we had at hand, although we started innovating in that in some of the areas. We used Java web application servers, object relational mapping, bespoke real engines, so on and so forth. And what we realized when we started with Leapsight is that we couldn't go this route again. I mean, starting to compile all these different technologies and try to work them to make them work together is difficult enough. And if we then need to be very, flexible and agile in order to anticipate what the consumer needs and in order to satisfy their needs, it's very difficult to do that in that particular environment. So what we decided to do is to create our own platform, and that's what we're going to try and cover as soon as possible. So a little bit of the history of this. So over the last 60 years, marketing has been evolving towards a higher resolution or fine-grained approaches. So from the lowest resolution that it was epitomized by Henry Ford's phrase, you can have any color of Model T as long as it's black, to the latest customer relationship management technologies and enabling this kind of marketing. Now, despite this, consumer-oriented marketing has always maintained a low-resolution push approach that regards consumers as passive targets of mass marketing campaigns. Now, even the state-of-the-art medium-resolution methods such as CRM, customer relationship management, are still rooted in this push approach. So basically, we all know all these tools existing today, and basically what they do is they organize the campaigns around pushing content in email, SMS, or personalization of content in websites. But there is no real understanding of what the consumer wants or needs, and there is no real development of a relationship between a brand and a consumer. Now, this push marketing, unfortunately, doesn't work anymore. The increasing number of channels enabled by technology and the technology revolution in the last decade has produced a fragmentation in media, which eroded the effectiveness and efficiency of this approach. Now, also in the last decade, internet, globalization, mobile, and social media have had a profound impact on the behavior of consumers. And these forces have generated an abundance of options and ease of access to information, which empowers these consumers to exercise unprecedented levels of choice. So it's very difficult to satisfy these consumers nowadays. And in trying to do that, marketeers are exaggerating claims about the performance and differentiation, and that leads to low trust in company-generated advertising. And more consumers trust their peers as opposed to the brands in terms of what the brand is and what it means to them. And word of mouth has become the most trusted form of advertising. So we had this problem before in a different way when we were working in the tobacco industry. Basically, media disappeared because we couldn't use it. So we realized we needed to use another means of engaging consumers. And we started using a pull approach. So basically, instead of pushing content to the consumers, we design a number of mechanics that we will use to get the consumer going or coming to the brand. And apart from that, the other key component is a mass customization of that brand experience. So we need to understand who this consumer is and go down to the individual consumer level and try to figure out what is it that this consumer wants. Now that is what we call high-resolution consumer engagement, and we've been doing that for more than 10 years. And we decided to create a company to exploit this opportunity and help other companies overcome the problems or similar problems, and also tap into this opportunity. Now, this kind of approach doesn't come without challenges. So we're talking about a real-time environment, high concurrency. Basically, you're talking about creating a platform and a capability similar to the ones that Facebook, Amazon, and the likes are using to engage each one of us. Now, traditional enterprise technology is not fit for purpose. You cannot use traditional databases and traditional application servers to do this, and that is what Google, Facebook, and the likes have already found out like 10 years ago. But what is most interesting about all this is that the future of marketing, therefore, is in distributed, concurrent, and dynamic and intelligent systems. And marketing, therefore, is becoming the most computational significant process in the enterprise. So let's see how we are trying to solve this problem today. I mean, if you work in a consumer goods company, this is probably your typical scenario, your typical architecture. So basically, you create new touch points to engage with the consumer, point of sales, applications, mobile applications, web, call center. You also use Facebook, Twitter, and social media to engage with them. But through all this, what basically is happening is that you have divergent capabilities in all these touch points. Probably all these touch points are using different technologies. The application, the mobile application is using a PHP backend, and the web is using a Java backend, and different databases. The data elements or the data models are not compatible, so I don't have a holistic view of the consumer through all the touch points, and I have different mechanics and different rules implemented in all these touch points, and therefore my capabilities are not the same. What this generates is a generic and irrelevant and inconsistent brand experience, and because trust is the most important thing when it comes to a relationship with the consumer, and because having an inconsistent experience is going to affect trust, this is a key component of the consumer engagement strategy. So how can we solve this? So 10 or 20 or 12 years ago, we solved this at BAT, and basically what we did is a platform that will handle all communication through all touchpoints. And basically, if you do that, you have a single point of access for all the consumer information, and you have a single point of access also to all the mechanics and all the capabilities. And that delivers obviously a customized, if you're intelligent enough, and relevant and consistent experience to that consumer. Now today we're going to concentrate on just one element of this, and that is what we call the shared knowledge space. And this is not only about data, but what we realized is that we needed more than data. We needed to store the rules, or we needed to have a more knowledge management approach to marketing. Now, this is all easy. We've done this before, so when we set to do this, we started with the same ideas and the same patterns and the same designs that we did 10 years ago. But then we realized a number of things. The first one is that today, the web is the database. This idea of creating your own database is obsolete, right? So if we are going to engage with consumers, we need to understand where these consumers are and what is information these consumers are living, what is the digital footprint of these consumers. They are living in Facebook and Twitter and YouTube and all these different websites. So our data management capability needs to be able to ingest this data from different sources that we don't control, and be able to amalgamate all of that and reason with that data. Now, the extreme challenge that this poses is that before in typical enterprise IT, what you will have is an ETL process, an extract, transform, and load process, or an ELT, and you will get all this data from different sources. You will transform that in a batch process, and then you will store that in a data warehouse. Now the challenge is, as you will see, this doesn't work anymore because of the number of sources that we have, because of the frequency of the data, and because of the volumes of the data as well. Another two elements that I'm going to refer to that we think that we learned in the past 15 years. So how can we cope with these? Well, fortunately, in order to do that, there are some guys that have already been working heavily on that. And the first thing that we need to consider is we need to delegate this type of work to the machine. If we follow the normal marketing route of, you know, putting people in the call center and sending people in responding emails and trying to respond to social media, that wouldn't work. So we need to be able to automate these using machines. Now, several companies have been producing a number of innovations throughout the last 10 years. And if you are an Erlang user, you probably heard about most of these in most of the recent presentations. And if you are a Bash or React key value store user, or a Cassandra user, or a MongoDB user, you will know all of these concepts as well. So basically what we took is we started working with this approach, trying to merge what we did before with this new world of technology. Now, just before we go into our technology development, a few more concepts to paint the picture of that, or to complete that context. So everybody knows about big data, and big data is defined today as a combination of any one of those things, right? The volume of information, the velocity of that information coming into our systems, and the variety of the information from different sources, different syntaxes, different schemas. Now, while doing consumer engagement, we learned two other elements, and they are key in being able to understand the consumer and engage properly with them. The fourth element is the veracity. Because of these different data sources, we need to understand that data is incomplete, is incorrect, and is ambiguous. Now, traditional systems don't know how to deal with this. A relational database is operates on a closed world assumption in which everything is true or false. Whatever is not in the database is false, and whatever is there is true. There are no degrees of completeness or correctness. And this is something that we need to fix if we want to deal with the world in the way it is. And the fifth element is validity. Now, the database, a normal database, will say this is valid, and this is valid forever. Now, we understood that this is not correct, and certain changes in the consumer, specifically lifestyle changes or life cycle changes, affect the way you need to care about that, you need to operate. And therefore, you need to be able to recognize when a fact about a consumer is valid, right? What is a period or interval in time in which this fact is valid? So just to clarify that a little bit more, imagine that you have this person is called Mary, and you gather information from Mary from different sources. So I have already stored information in my database, I gather information from Facebook, Twitter, Google, and I find a number of issues there. So the first thing is that, according to our database, Mary is married, right? But according to her profile in Facebook, which was updated 1 week ago, she's not. Right, so what shall we do? Now, it depends on who we are, what is the product that we're trying to sell and communicate, or what the brands try to communicate. But it might be the case that that attribute is very important to us, and it might have legal implications. So it is very important to us to be able to isolate these two facts, be able to associate metadata to these facts, and when I'm going to reason about the facts, be able to use whatever information, whatever fact is right for the occasion, right? So basically what we need to add to this is a provenance capability. So I need to separate these elements in different namespaces so that I can flag and say, well, this is data that I brought from Facebook, this is data that I store, or Mary has gone through some kind of registration in our website or in our touch points, and she left that data with us. But also I need to associate what is the degree of veracity or accuracy or probability. So I'm going to say now that, because, we've had a long relationship with Mary and we know she's been married for a long time, we're going to say that we trust our data a lot, so that's 100% veracity. Now, Facebook, we don't know really. We need to try that out. In the case of Mary, we're not so sure, and therefore we're going to flag this with a 70%. Apart from that, I need to say at least that this record is valid since this moment in time. We're going to see later on that there are other ways in which we can do that, and more information that we can actually store. And just to complete this picture, so fine, so we have this data complexity, and big data is one element. We can take the 5 elements that we showed before, and we have a complete big data framework that we can work with and say, fantastic, so we have now the means of and the understanding to be able to gather all this information. Now, there are 2 other elements that we mentioned before that come together and create the perfect storm, and those are the business logic complexity. Remember, we're moving away from push and into pull, and we need to develop new kind of mechanics to engage with consumers. And those mechanics can be loyalty programs, raffles, instant wins, but the key aspect or the key connotation of these is that basically I am multiplying my business logic complexity, both from the management of the business logic in hands of the marketeers, but also from the development environment for the developers. And apart from that, we have the real-time and always-on capabilities, right? So the listing these consumers want nowadays, because they're now used to Amazon and Facebook and all these different platforms, they don't want they don't want to be interrupted in their operations or the way when they are engaging with the brand. So basically what you need is all these touch points up and running all the time. Now, big data is not solving that issue. Big data is just a fantastic way of generating insights. But what is lacking in marketing is the capability to react in real time. So the typical issue that we have in marketing is not big data. Everybody's jumping into big data bag and investing in big data. But the issue is most of the marketeers have no means of executing that or the insights that generate with that. And therefore, we decided to concentrate on this aspect, which is what we solved 15 years ago in a different way with different technologies. And what we learn is there are 2 main loops, and this is an oversimplification of our blueprint, but basically there are 2 main loops. We need to completely automate the interaction with the consumers. But every time we interact with them, we need to feed our knowledge base so that we can start learning and adapt. And that's the second loop that we call the learning loop. And in order for these loops to be working together and to be able to do this and to react in real time, we need to share this knowledge space between them. And this is completely different to what CRM technologies have been doing the last 20 years. CRM talks about operational CRM and analytics CRM, and you have the operational data store, and you have the data warehouse, and then you have processes that move data from data warehouse in a batch way into the transactional one. That we've proven that doesn't work anymore, right? So what we needed to do, what we did at that point in time, is basically generate data marts on the fly using an off-the-shelf BI solution. But what we decided to do this time is, because of all the elements that we mentioned before, is to create a new kind of platform that can enable this architecture blueprint naturally. And for that, what we need is basically this automation loop to respond to events as they occur, feed that using the knowledge base to do that. That what it means is I need to use the data and the rules that I already learned to be able to automate that interaction with the consumer. I'm gathering those events as well, and I'm going to use big data in the learning loop to generate more insights, and I'm going to feed that into the knowledge space with more data, more facts, some of them summarized, but also with new rules. So we form a kind of continuum that orchestrates all these two loops to be able to satisfy the needs of the consumer. Now, which are the requirements for this thing? So basically we're talking about dynamic data model. Because we are engaging with the consumers and we don't, most importantly, when we start doing this, we don't know exactly what information, what facts we need to store about the consumer. So we need to be able to change that very quickly. Now, if we went for an architecture that uses a traditional relational database plus object relational mapping plus middleware, every time we change the data model, we need to change all the different stacks, and that is too slow for a marketeer. By the time we finished with all of these, it took us 6 months, and the opportunity for the marketeer disappeared. The second element is relationships. We live now in the world of highly connected data. This is not only because of social media and because of the importance of word of mouth and the importance of being able to map who are the friends of these consumers and what is the influence this consumer has in his own network, but also increasingly we have devices that connect with other devices and with people. So we need these new graph capabilities, this capability to relate everything to everything. And we also need this data layer to be programmable, ideally functional, relational, and logic, right? Because it's the right way, is a declarative right way to do that. In addition, we need low latency, and we can achieve that by eliminating that impedance mismatch that we talked before. The relational database, the object relational mapping, the rules, all of those require bridges to be built between them to be able to work together. And that adds latency. And finally, we need to deal with the 5 V's. So with the ambiguity, with the uncertainty, with the validity, plus the availability and of the attachments. So basically, because of this, we created the Leapsight Semantic Dataspace, or LSD for short. And by the time we did this, we thought really this was like marketing on acid. So we've been dreaming about this platform for the last 10 years, and we couldn't do it in the corporate environment, and we left that corporate environment to be able to realize our dream to build this. So what is LSD? So LSD is a distributed, scalable, fault-tolerant, deductive semantic data space. Now I'm going to go into each one of the elements. I'm going to start digging into. I'm going to then try and do some brief demos to show you what we're talking about. So LSD is masterless and it's sure nothing. So basically, you create a cluster of nodes, and those nodes have no master. They're peer-to-peer. They replicate data using peer-to-peer synchronization. And we, in the case of LSD, we adopted the eventual consistency model. And this is very interesting because we started working with this when all this idea of eventual consistency was being challenged as well. And to us was really important because in our world, what we want to do is to be able to create a knowledge base per consumer, right? I'm not interested in processes at the beginning. We're not interested in processes that span multiple consumers. Those are processes that typically are batch. Typically, you won't use transactions to do those because they're too heavy anyway. If you try to do those using the best transactional technology out there, it wouldn't work. So, flagging all these millions of consumers in batch, is something that you do, and you don't use transactions at all. Now, when I need to engage with the consumer, what I want is actually to create a virtual database for that consumer alone, right? So my requirement on the strong consistency and transactions is relaxed already. Plus, I want this to be up and running 100% of the time. So I don't want the consumer to miss anything, and therefore, what we want is at least to have the capability to do eventual consistency, and in the future maybe go into stronger models. It is scalable. I can scale this cluster by adding new nodes in the similar way to what other NoSQL database will, and obviously we can use commodity hardware. Now, the other element is the fault tolerance, and that's why one of the main reasons why we selected Erlang to do this. So what we want to deliver is continuous availability, no single point of failure, and we use hinted handoff and anti-entropy mechanisms to do self-healing. Now, this might ring a bell if you're an Erlang user or React user, and basically it's because we are using React Core, which is an open source Erlang library that helps you build these kind of systems using the Dynamo architecture that was defined and described by Amazon, and they use it for the design of their shopping cart and other services inside Amazon. They're still running. Finally, as opposed to all the other databases that you might have seen, this is a deductive database. So basically, we can create rules and query those rules, and using those rules, we're going to generate new data for you. For that, we created Leaplog, which is a domain-specific language. It's based on Datalog, which is a declarative query and logic programming language. It's compatible with the relational algebra, and as you will see, is even more powerful than SQL if you provide some extensions to that language. In terms of the semantic aspect, what we decided to do is to base our information model on the resource description framework, which is the technology behind the semantic web. And basically, this is a knowledge representation language, but it's also a directed label graph. And when we were talking about relationships before, because we want to relate everything to everything, this was the right model. Plus, if you want to bring data from sources like Facebook already supports RDF. So that simplifies a lot the interaction and integration of data from these sources. Finally, in terms of the data space, so this is a database of facts and relationships. If you come from the relational database model, this is a relational database in which we deal only with a universal relation. That is, there are no n-ary relationships or relations in this database. It's a single way atomic fact that we can store, and we're going to show you that in a minute. And it's also a multi-graph database. So let's jump into a little bit more of the details of how we do this. We're going to start talking about the information model and then the distributed scalable and fault tolerance aspects of data space, and where we're going to go into the didactic and semantic elements of it. So the information model, if you're familiar with the enterprise entity attribute value or model or the resource description framework, I can talk about anything and express facts about everything just by using a triple, right? A tuple with 3 elements: subject, predicate, and object. In this case, because we're adopting the RDF specification, those subject, predicate, and object have different types. So probably this one is the most technical slides in the presentation, but basically there is a type system that you can use, and basically the subject is as a URI, as an anonymous resource. I'm going to give you some examples right now that allows you to identify something or somebody. A predicate is another URI that is going to show you, is going to talk about the properties or the attributes of that entity. And the object can be another subject or can be a value. So I'm going to try and now go into the LSD environment to show you an example of how we can use the LSD environment to do this. All right. Fine. So hopefully you're gonna all see that. I've just launched a node, an LSD node. I'm in an Erlang console. What I'm going to show you right now is just a little bit of how we deal with those resources. So let's say that I want to talk about Leapsight. So what I'm going to do is I'm going to create a resource that is Leapsight, and that creates a data structure that we are going to use internally. I'm going to say also that I'm going to use some elements from the RDF specification. I'm going to say there is a property called type. Now that's an internal property, is a built-in property, and therefore is going to be represented by an Erlang atom. That is in order to say, because we're going to use this property a lot because it's part of the RDF language, we're going to simplify that by using atoms. I can also create literals, as we said before. So in this case, a number is an integer. That integer is going to be represented internally as an Erlang integer. In the case I wrap that with strings, that's going to work again because I'm forcing it to literal. If you're coming from Erlang and you want to represent the PID as well, the PID is going to be represented in the same way. Now, if you take a date, for example, that is a way we want to represent the date. And just to comply with the RDF specification, if I write an integer and I specify that is an integer, I'm going to get that integer again. But if I go and say I'm going to use the XSD, the XML data types int as opposed to integer, I'm going to flag that with metadata. So that is a way we create, in principle, all these elements that we were talking about in the presentation. So we're going to go back to the presentation. So there are more elements that we need to add in order to create a statement. And a statement is a fact about an entity. So what we defined before is that we wanted to respect or isolate the data from different sources. So for that, we need a fourth element. So this is beyond the resource description framework. But also, if we want to gather information about the certainty, we need to add another element, which is the certainty degree. And finally, what we want to also store is when this information was recorded, right? So in order to do this, we're going to use what we call a transaction ID. This is a lexicographically k-order ID that we're going to use in several ways throughout the LSD, and we're going to see how. So let's say that we want to represent that information that we've spoken before. So we're going to assign a URI to Mary. Let's say it's the ID 123. We're going to define a predicate that is called the full first name. And we're going to assign the object Mary, the string Mary, as a value. And we're going to store that in the consumer profile with 100% degree. And a minute ago, that transaction is going to be assigned. And I can do the same for all this information that I have from Mary. She's married according to us in the same graph, but according to Facebook, I have more information. So I have a friend from Mary. That is the ID 124. 124 itself is being described as well with the first name and Kate. So another way of talking about this is by drawing a graph. So, and this is exactly why we've chosen this representation. So in this way, what I have is a homogeneous way of representing any relationship. So relations between people and things have the same shape as descriptions of those elements. So basically what I'm doing here is saying the same that I'm doing before. Now, for each one of those statements, I'm going to add the degree and the transaction ID, but I'm going to skip. I'm going to just show you that in the case of that middle statement. I'm not going to do that for the rest. But also, I'm going to flag that this is what happens. So what happens is I'm describing Mary in different graphs. And as you will see, I can then go and query those different graphs. And I can merge the information from those different graphs as well. So how this all works is basically we store those statements in graphs. Those graphs live in logical spaces, and those logical spaces live in tenancies. So all of this is logical. The only thing that we're going to store is a statement, and out of the statement we're going to get all the structure for us. Now what we can do with this kind of API is, at this level, is we can write, remove, read all this data. Now we have 4 different elements for dealing with writing and removing. So writing a statement, basically when we write a statement, we are actually not writing the statement itself. As we're going to see in another slide in a more technical definition of it, we're writing actually indices that will allow us to query the data in any way we like. And in basic configuration, we can store up to 6 indices. These are indices that are covering indices, so they store the data. They're not pointers to the original data. They actually store the data, and they provide different collation orders. So in the case of the 6 indices, the first one, for example, will store the graph, followed by the subject, followed by the predicate, followed by the object. That allows you to, for example, query the graph with wildcards for subject, predicate, and object, or query the graph with the subject and wildcards for predicate and object, so on and so forth. Now, every time we write, we're appending the data. We're not removing. This is not an update in place. So we never delete and we never update data. The only thing we do is we append data. The remove is actually a write with a degree of 0. So when you write a statement, you typically write a statement with a degree that is between 0 and 1, meaning 0, more than 0% and 100%. But if you write a statement with a degree of 0, it means it's a Thompson. You're logically deleting that statement. Now the write is idempotent for the same combination of SPOG within the same transaction ID. So if I want to write two things with the same SPOG and D, actually that won't work. So only one will be written, which is what we want, because stating one thing several times doesn't change the fact. And in the same way if you deal with the eventual consistency in React, KV, and in Cassandra and in other systems, we do here. So we allow you to define how many replicas are you going to have for this cluster. Let's say we have 3 replicas, and then every time you do a write, you're gonna configure how many acknowledges you want from the 3 replicas. Do you want 1, 2, or 3? Those configurations are on a per operation basis. So every time I do a write, a remove, or an async write and an async remove, I'm going to get that. In the case of the async operations, basically I am getting back a future. I can carry on doing what I want to do, and then I can check whether the result has been received. So a typical write will happen like that. I need to have a client. I'm using Erlang as a client here, so I'm going to write a number of statements. In this case, I'm going to write 2 statements that are actually equal in terms of the SPO and G, and because of that, the first one is not going to be written, because the first one was the only difference between the 2 is the degree, and basically I'm gonna write only the second one. In the case of reads, basically the way we read in this API is by using pattern matching. So basically I'm going to create a statement with wildcards. I'm going to use that to read the data from the store. In the same case as write, I can do an async read as well. And then what I have is a take. A take is a read that actually removes the statement from the store, right? So every time I do a take, what I'm doing is a remove and a read. All of these APIs return and operate on statements. There are no projections as you can do with SQL. We're going to do that using another API. And then history, what does is that includes all the versions that you can get from that result. So every time you read, you're going to read information from the space. If that was deleted, the information will be nil. But if I want the history of what happened to that statement, I can use history to do that. So how I create a pattern, basically I use the API to create a pattern. I use wildcards and variables and constants. In this case, what I'm saying is, for example, I want to bring all the subjects whose predicate age is more or is less than 21. So basically I'm trying to find out, in this case, consumers that are less than 21 years old. But also I'm going to use at least a 0.5 or 50% degree certainty in this case. So let's do now a demo of how we can do this here. I'm going to resort to some data that I have here. So the first thing I'm going to do is I'm going to create a client. right? So the other thing I'm going to do is I'm going to create a number of statements. I'm going to say that there is a graph G. I'm going to, the way we store graphs is using a particular URI. I'm going to make this a little bit bigger. We use a particular URI that is using LSE as a specifier. Then we use the space name on the graph name. So basically, this means store in LSE. In my tenancy, which in this case is Leapsight, I'm going to create a space called ESL, and I'm going to create a graph called G. Then using Erlang, I'm going to define 4 resources. Joe Armstrong, Mike Williams, Robert Verding, Klaus Wisdom. These are the guys who created Erlang. I'm going to create the resources. Oh, sorry, that is a. So before I do that, what I need to do is I am using, at this point in time, I am using a prefix max. So I don't want to write all the time all these long URIs. So what I'm going to use is a way of getting these URIs a shorter way. So basically I created a prefix mapping, right? In that prefix mapping, I created a demo prefix. Now I'm going to define again my resources. I am going to say that PM equals PM0. Sorry. PM equals PM0. Fine. Now I'm going to create the resources. As you will see, the previous resources were using a short denomination. So basically, I'm using short queries or short URIs. So now demo is going to be expanded into a full URI here by using the prefix mapping in here. Now what I'm going to do is I'm going to create a statement. So the way I create a statement is by using the API. I create a statement and say, well, the subject, in this case, each one of the gang of 4, I'm going to create a statement for each one of them saying that they created Erlang, right? And I'm going to write that in this graph G, and I'm going to say that I know that for sure is 100% true. So what I get back is a number of statements. Now these statements are not stored in the dataspace yet because I haven't issued a write. So these are in memory. So what I have now is a list of the statements for each one of the Erlang creators saying that they created Erlang. Also, I'm going to create another resource. I'm going to create a resource named Francesco Cesarini, the founder of Erlang Solutions. And now I'm going to say that obviously Francesco knows all of these guys, right? So I'm going to create now a series of statements saying Francesco knows all the subjects in the gang of 4, right? So what I get is a list of statements saying Francesco knows all these guys. Now I'm going to do a write. So I have statements 2 and statement 1's variables mapping all these statements. I'm going to write the statements 1. Sorry, that's client 0 I used before, so I'm going to use client. If you're not familiar with Erlang, Erlang doesn't have it's a single variable assignment, and therefore I'm messing around with that at this point. Perfect. So we're going to do that again. That's it. So we just created in this case 4 statements, and we've written that 3 times into the store. Now we're going to write the other statements saying that Francesco Cesarini knows these guys, and we have all that now. Now what I can do now is create a pattern, and I'm going to say that I want to know who knows who in the graph G. And we had it before, but I can actually do this and say is LSD is the LSD ESL demo, and I'm not interested in the degree, so any degree will make it. Right, so those have been expanded because I have the prefix mapping installed. Now I'm going to do a read, so I'm going to use a client. I'm going to say read client, and I'm going to use P as a pattern to read the data. Now what I get back is, again, the information that I stored before. In this case, Francesco knows all these guys. Now I can actually say carry on with the pattern. I can do any pattern I like. So I'm going to just copy these, and I'm going to start changing some of those queries. So instead of doing this with a variable, I'm going to do it in line. I'm going to create a pattern, and I'm going to say, well, bring me everything about this or anything that is stored in this graph. So I'm going to get not only that Francesco knows these guys, but also that each one of the guys are the creators of Erlang, right? So basically what I can do with the pattern is, match anywhere I like all this information. I can actually, for example, say Francesco Cesarini. If I want to just bring the information about Francesco, I'm going to say demo Francesco Cesarini, right? And I can actually say, well, in any graph. In this case, Francesco is only in one graph, so I'm going to get only the information from Francesco in that graph. Right. So that is how I read and write information in the space. I can actually go a little bit further and use some patterns, but some conditions in patterns, but I'm going to skip that and go back to a more interesting way of looking at that. So going back to the presentation, we're going to go a little bit into the technical architecture of this system. So basically, this is the way it is implemented. We're using React Core as the distribution framework, and we're using the React Core patterns, which means that what you have is basically, if you look at the boxes below, we have a vnode master that is orchestrating the work with different vnodes. Now, this is a very clever design did by Amazon and a very clever implementation built by Basho on top of Erlang. So basically what it means is that as all these nodes might fail, I need another level of indirection. I need to be able to store data in virtual nodes, and those virtual nodes can move from node to node in order to satisfy the requirements for high availability. Now, what we're going to do is we're going to split all the cluster in a ring, in a consistent hashing ring, and that is all done by React Core. And we're going to store all this information. I'm going to show you how we store this information in the next slide. So basically, you interact with these through a client. It can be an HTTP or protocol buffers, and we interact with the API that we just seen. Now we've just seen the Dataspace API. I'm not going to show you the object or the graph API, which are just elaborations on top of the Dataspace API. But I'm going to show you something that we call liblog in a number of slides. But before doing that, just wanted to show you how this works in a little bit more detail. So basically, I can scale out this platform by adding nodes. This is exactly the same in the same way that React KV works, because React KV is using React Core. Now, every one of these nodes is going to store the data in main memory. We have a number of backend storage engines. The main one is ETS, but we are experimenting with another set of options that will probably bring the memory consumption down. we're using a term dictionary compression. So in every one of those vnodes, we are sharing those URIs, those lengthy URIs and those elements. So we're compressing the store by sharing all those elements in a dictionary. And we assign an ID to each one of the dictionaries, and therefore what we store in the indices are pointers to that dictionary. We use command logging to persist every time you write. So every time you write, we're logging the transaction, not the data. So in the case of a failure, we can go back up, read that command logging, and reapply the transactions. We're using snapshots to disks, and increasingly we're moving into snapshots to level DB, because what we're planning to do is to add disk-based graphs with level DB and history disk archiving with level DB. So basically all the data in disk following this will be in level DB and will be queryable in level DB as well. But obviously the performance that we're trying to get is because what we're trying to do is reasoning with the data, as you will see in a couple of slides. We need the data in memory. Plus, what we learned so far is that in our previous environment, we needed to cache at least 70% of the data. So what we decided is, let's go for an in-memory technology. This is the right way to go in the future. So let's optimize for that environment first. Now, how we store all this data. The statements are stored in covering indices, as we mentioned before. We distribute these using consistency hashing. So I'm going to show you how we do that. So every time you write one of these statements, we're actually generating between 3 and 6 covering indices, and those indices are going to be stored in n number of copies. So if we say that by default we're storing these in 3, so I want a factor of replication factor of 3, I'm going to end up writing this into at least 3 vnodes per index, right? So this means that basically we're reaching 16 different partitions if I am using the 6 covering indices. So in order to be able to do this efficiently, the best way to do that is to limit operations, write operations per graph. Now, we don't stop you from writing to multiple graphs, but that might mean that you're inundating all these vnodes at the same time, right? So we're going to come up with another option that is basically using a stronger transaction approach, and we'll limit that to 3 participants in that, so 3 vnodes in that operation. So you have the options to, if you write by graph, so you're reaching typically a fewer number of nodes. If you want to write to multiple graphs in the same operation, then you're reaching multiple nodes, and that might be an issue. So you want to take care of that. In terms of anti-entropy, so what happens when I write and one replica didn't receive the copy, and then when I read, well, depending on the configuration of the consistency that I want, if I say that I want 3 copies out of the 3 copies that I should have stored, then what's happening in this case is every query that I issue to these vnodes is going to be signed digitally. We're using a Merkle tree to do that, and we're not signing the content of the result. We're actually signing everything that was required to create the result. So in the case of more complex queries, and in the case of queries that involve multiple versions of a statement, are including tombstones, basically we're including all of that to make sure that when we say that these are exactly same replicas, they are at all levels, not at the level of the result only, but at the level of the base data storing that in the vnode. And in the case of a conflict, then what we can do is we can issue a read repair by playing back that transaction ID from the replica nodes, from this particular node that was missing data. And we are enhancing this by using active anti-entropy in the same way that React KV is using it now. So finally, we're going into the more interesting aspect, which is the deductive semantic dataspace. Now, hopefully, if we have enough time, we can do a demo about this. But basically, this is the real reason why we did all this. So in order to be able to do that, we define something we call liblog. Now, liblog is language that is based on Datalog. Now, a quick overview of Datalog in 2 slides. So Datalog is a query language. It's actually a logic programming and query language. And it's a subset of Prolog, which is a logic, is the logic programming language. Now, for those interested in these technical aspects, so Prolog is a Turing complete programming language. Datalog is not. So you cannot use Datalog as a general purpose programming language. So therefore, for us, it's going to be a domain-specific language that we're going to use to define business rules, so the logic that we want to operate, and the data, and the queries that we're going to use against that data and rules. Datalog is one of the most researched non-commercialized technologies in the world, probably. I mean, most of the innovations in SQL technology is actually deriving from Datalog, but the vendors moved away from Datalog in the early 80s because they thought, SQL was all that we needed. Now, for those of you very technical, you will know that SQL by definition doesn't allow recursion. Now, DB2 is one of the IBM DB2 is one of the databases that, and I think the Microsoft SQL also implemented recursion that is based on Datalog. Now, several extensions exist for Datalog, which include negation, arithmetic comparisons, function symbols, and aggregates, and we're going to see how those works. Now, if we take Datalog and negation, we can get a language that is more expressive than SQL. Now, this is how Datalog typically looks like, and I'm going to go rapidly into each one of the elements. So what we have here is what we call a rule. A rule has a head or a goal. It has an implication symbol, and then it has a body. So basically, this rule says if there exists a tuple or relation in the data in somewhere, father xy, that means that either in this case that y is the father of x, then it means that y is the ancestor of x, right? So to go a little bit more detail, ancestor, father are what we call predicates, right? And you can think of those as the name of the table in the database, in the relational database. So what I'm saying here is that if you find somewhere, either by another rule or in the database, a relation, i.e. a row in a table father for x and y, then I derive the fact that y is the ancestor of x. Now, in order to be able to calculate the ancestor, I need another rule. And I'm going to use a second rule that says that if y is the father of x and z is the ancestor of y, then z is also the ancestor of x. In this case, I'm using what is called a conjunction. So I have two atoms or two subgoals separated by a comma. The comma means an and. So basically what I'm saying is, if there is a father xy and an ancestor yz, then there is an ancestor xz. And then I'm going to do an assert. I'm going to say, it is true that John is the father of Tom. And then I'm going to ask a query, and I'm going to say, who is Tom's father? And the answer is going to be John. It's going to be John. Who's the ancestor? It's going to be John, because John is Tom's father, and because of the rule 1 and rule 2, John is also the ancestor of Tom, right? So that is the way you work with Datalog. And what we call the first two rules, the assertion and the query, we call that a program, and that's what we're going to use in Liblog to define the logic. So what we thought about this, we thought, this is the right technology to use in marketing. In marketing, I need to change data constantly. So the data space allows me to do that. I can create statements, facts, without actually defining what a table is, without defining columns, and I just write whatever I want in the data space. Those are flat tuples, so there is no way I can make a mistake there. Everything is atomic, so I'm going to store all these facts there. But then I need to be able to also move very quickly in terms of marketing and define all this business logic and the complex business logic that I want to use. And what about testing all this different business logic in real time? I need to change that business logic very quickly. If every time I want to change the logic, I need to go and hard code something in Java and compile it, it's going to take a while. So what we wanted to do is to start using logic to be able to express those kind of rules. Now, before when we build this platform, we use our own bespoke rule engine that we build in order to overcome the limitations of the compile cycle. But nowadays, we obviously defined and we found out that Datalog was the best approach for this. So what is Leapsight then? So Leapsight, as I said, is a Datalog-based language. We adapted it to work with RDF. LSD can make deductions based on the rules expressed in Leapsight. We use a top-down set-oriented evaluation. We provide built-in predicates, and we're starting to provide now function symbols as well, but those are built-in functions, so we created some functions to manipulate some of the resources. We still don't allow you to define your own functions, so you can do that outside in whatever language that you're using to consume the results. We haven't got negation and aggregates, but we're planning to add that. So an aggregate will be, for example, counting all the results or adding or calculating averages or means on a result. So in terms of the Leapsight syntax, is very similar to Datalog. So basically what we do is, in this case, is say, well, because we're storing these facts, the only predicate that can exist in the database is the statement predicate. And because we don't want you to write statement, constantly, that is implicit. So if you write a tuple with 4 elements in this case, I'm not going to cover how we deal with degree, but we deal with degree as well. That's part of the syntax, but I didn't want to complicate the presentation. So basically what we do is here is saying, well, there's gonna exist the ancestor y of x in the graph G if there exists a statement of the shape of x foo father y in the graph G, right? And then I can actually query for that ancestor, but I can also generate statements out of the rules, which I'm not showing in this case. So let me show you how we deal with queries then. Let's say that we want to do the same query that we did before. I'm going to simplify this. I'm going to say, I'm going to use another API. So instead of using read, now I'm going to use select, right? And I'm going to say, I'm going to call the select function. I'm going to say, I want to select everybody. I'm going to send this the same demo that I did before. Very simple. I'm going to just grab all the data from a graph. So I'm going to say, I'm going to write the data log in as a string. Now the select function will pass the string, will validate that data log, that leaplog syntax, and will execute the query. So we're going to say, I'm going to bring all the S, P's, and O's in the graph LSD ESL demo. Right. Now, what I get in this case is I'm not getting statements. What I'm getting is a projection, right? What I'm getting is, because I haven't said what the projection is, and I'm going to show you how you can do that. By definition, this query is going to project in these 3 variables, S, P, and O, right? I'm going to have the variables here. So the head of this result set says the variables projected are the S, P, and O, and the values associated with S, P, and O are each one of these. So I get all the rows, right? Now, let's say that I wanted just to know who is in this graph, right? Who are the objects in, or the subjects in this graph. I can actually say this. I can come here and say, I just want to project out the graph. I'm going to use the same syntax that I use for rules. And now I'm going to do that again. I'm just getting the binding for the S variable, right? I can obviously do S and O, and I'm going to complicate these and say, well, let's say I want to know who knows who, so I'm going to say demo knows, and I'm going to just get that Francesca knows Mike, Joe, Claes, and Robert, right? So this is a very, very simple and best way to query, but I'm not getting statements. The reason why I'm not getting statements is A, because I'm projecting out, and the second reason is I might be deriving, as we will try and see if we have enough time, we might be deriving data from rules, and therefore, if you want to derive data from rules, I don't want to create statements unless I explicitly want to do that, in which case I need to use another API. So let me see if I can bring that up and say, okay, I'm gonna create a rule. I thought I had it here. Yeah, I'm gonna create a rule here. Let's see if we can use another element. I'm gonna show you something else, which is a preliminary web client that we have. So let's say that I'm gonna do the same query here. Oh no, I'm doing something wrong. Oh no, the server is not active. Sorry guys, I'm gonna go back to this one. So I'm gonna write a rule that says the following. See if it works. This is when everything collapses. So I'm going to write a rule 1 that says this. Right. So what I'm going to say here is, if there is a tuple is a statement in any graph that says that a subject, I'm going to use S here, is a creator. Let's complicate that. Right. So what I'm going to say here is that if there is a subject who is a creator of something, right, and there is another subject that is a creator of the same thing, and those two subjects are not the same subject, then these two subjects are colleagues, right? So I'm going to write that rule, and I'm going to apply that here. Sorry. Yeah. I knew this would happen. Sorry, we're going to use that prefix here. Good. R1. No, there's something wrong here with my environment, guys. Sorry about that. Let's try and do that. Let me try and fix that and see if it and make it work. No, it's not working. So I have something funny with my environment here that is not working. So So back to the presentation. So basically, sorry. So basically, what we want to do with this is generate new facts out of the rules and the facts I already have in place. The challenge that we have with RDF is obviously that the statement is I can derive statements, so I can store statements, I can derive statements. So Datalog actually doesn't allow you to do that. So in order to do that, we needed to overcome that. And unfortunately, I have a broken environment. I cannot show you how it works. So that's it for LSD, and basically we are starting to work with a number of customers in the space of defining this kind of environment for marketing, and we obviously we are early on in the implementation of these as a product, and we're looking for people like you to become early adopters and working with Erlang Solutions as worldwide resellers to be able to reach the market with these. We're very flexible in terms of the no licensing support and consulting, and we are going to be offering a community edition soon. We're going to start doing that very limited because we have obviously we're starting up with these. We have limited resources, and basically that's it. I mean, we are interested in understanding how do you see these in your environment. We build this for a marketing environment in which we want to reason about every consumer one consumer at a time. We do not intend this solution to be a solution to compete with high performance query engines or high performance databases like VaultDB, which they have a niche and which require probably to know in anticipation what is a query that you want to do. So what we want to do with this is basically be able to be very flexible in the way we store data and be able to be very flexible in the way we collect the data as well, and we use the rules to generate this.
Excellent. Well, I'm sure that everyone who has participated in the webinar will join me in thanking yourself, Alejandro, for a very inspiring talk on the Leapsight Semantic Dataspace technology. We have crossed over the time that we had available for the webinar, but to be fair to our audience and to the many questions we've received, first of all, I have to say that because we've gone over the time, we won't be able to answer all the questions, but we should try and at least answer a couple of them. And as we said previously, my details and our details are on this last slide. You're welcome to send us emails and ask additional questions, and we'll obviously answer questions that have arrived that we can't answer now at a later time and via email. But to honor the questions that we've received, at least a few of them, Alejandro, one of the questions that has sort of come forward, and you've answered many of these through your presentation, but a bit of a broader question in the sense of how do you see Leapsight Semantic Dataspace developing and evolving going forward? What is it missing at this point that you sort of wish to add to it in the future? How do you see the technology progressing in time ahead?
So basically, there are a number of elements. The first element is optimization of very large rule sets. So at the moment, we have a number of optimizations implemented, but again, we are focusing on reasoning one consumer at a time. When you want to reason with much more data and more complicated queries, we need to think about more optimizations. So we have two ways of optimizing. Thanks to Erlang, one optimization is parallelizing even more the queries. So obviously I haven't shown you, and I have this broken environment, but I haven't shown you these in terms of performance. But we can deal with normal queries, simple queries in milliseconds. a simple retrieve of thousands of statements is about 3 milliseconds. Reasoning goes up to 20, 30 milliseconds. But if you want to do a very, very complex query with a lot of rules, then it gets complicated. So one element is to optimize that. And the second one is in terms of providing more element or more options in terms of consistency. So we adopted the eventual consistency, but we know that we need to go into stronger consistency elements for some of the use cases. Fortunately, we have React Core as a base, and because React Core 2.0 is just about to be released, we're going to get more elements in terms of that. So commutative replicated data types or stronger consistency options that we might be able to use out of the box, and that is, I guess, the second key element. And probably the third element is improve, as I said, I think in the last slide, and sorry because we ran out of time. In the last slide, I was saying one of the elements was enhancing also durability, so more performance in terms of the checkpointing of data and recovery of data.
Thank you, Alejandro. Another question that has come through, and one that I think is quite interesting in terms of viability of LSD. Could you tell us a bit, how does LSD perform in terms of OPEX and CAPEX in a large, for example, FMCG environment when you're supposed to be addressing millions of consumers? What's the cost of setting it up? What's the cost of running it? How do you see this from that kind of business perspective?
Okay, so basically we have a number of different business models. So we build this technology to be part of an asset that we develop to define as several solutions as a service you want. So one of the things that we bring into market is not just this technology. This technology was our brainchild and what we wanted to use to be able to build the consumer engagement platforms that we're offering. So if we're building a consumer engagement platform for you, then the LSD will be part of that solution embedded in. And typically, our business plan and the reason why we created Leapsight is based on our experience in doing this with millions of consumers, and we think that we can get back to a number of something between $1 and $2 per consumer per year for all the platform software infrastructure running, including the LSD running inside, right? So we're tackling this from a business case point of view, not from a technology selling point of view. So from a business case point of view, we think that we can enable a platform that will cost to operate, to build, to run, including all the licenses of our software and other software that we might need, plus the infrastructure. We can make it to run in between $1 and $2 per consumer per year. And now, in a typical consumer goods company, that means that you will pay that with 10 transactions. So if you are a cola, a Coca-Cola, a Pepsi, or a Unilever, or a tobacco company, you might cover that cost by selling 6 units, right? And more if the whole operation, if the whole consumer engagement strategy is the one that generates that, then it's basically for free. And in order to be able to do that is the reason why we came to Erlang and to React Core and to a technology that we're developing, because you cannot do it with traditional enterprise technology. That wouldn't be affordable.
Thank you, Alejandro. Again, many apologies. We've received so many questions during your talk, and we'll only be able to honor a few of them due to the time that has expired. The one thing I would like to ask you is, in terms of the rules you've set and the artificial intelligence in place, how would you say relevant and accurate typically are the conclusions that the system creates about any individual consumer, given the complexity and dynamics of data? You've addressed this partly during your talk, but has this ever been tested and verified? Can you sort of guarantee or give us at least a sense of how accurate a typical conclusion is when you're dealing with millions of consumers and obviously creating these tailored campaigns?
Okay, so basically, remember that when you deal, and based on our design and based on our experience, the way to tackle this is by reasoning a consumer at a time. So I need to prepare the knowledge base. I might decide to use, machine learning and data mining, stuff that we did before, to analyze the data in a bulk. I'm going to analyze all this data. I'm going to generate facts about these consumers. But then I'm going to generate rules that will operate on these facts. Now, when I'm going to engage a consumer, or the consumer is engaging us, and I'm having an interaction through a web or a mobile application or whatever, what is going to happen is I'm going to reason only with the data from that consumer. So what I'm going to do is I'm going to create, from an Erlang point of view, what I'm going to create is a process that represents that consumer, and I'm going to start consuming the data and applying rules to that consumer. Now, one thing that I didn't cover, which is interesting, is that I can use a complete different rule set per consumer. So the way we design this is so that I can not only change business logic by changing data, but I can change business logic by changing the logic. So basically it means I can write a single application per consumer. How do I do that? I do an application that writes applications for me, right? So I do an application that, based on machine learning or based on big data, or whatever analysis you want, it will write not only data, but will write rules. Now, the rules are there just deriving what is in the store. So it's very, this framework, this logic framework has been proven. Now, the element that I haven't shown you, which is very early days, is how do we use the probability degree to derive knowledge. And for that, we need to go into stuff like Bayesian networks that are a little bit more complex. So it is not as simple as a multiplication of a probability of multiple of a join in order to derive that. So in terms of the correctness, if you write the rules and the rules are right, you will always derive the same results and given the same data and the same rules, you will always derive the same data, assuming that you're not messing around with degrees of probability. If you're messing around with that, then it will depend on the algorithm that you use, or that we use, to calculate the compound degree of something, right? And for that are many options. There are simple probabilistic multiplication, but then you have Bayesian networks approach and Markov chain approach, which we haven't implemented yet.
Thank you, Alejandro. We have Robert asking a question. How does Leapsight Semantic Dataspace deal with various privacy protection and rules in place, and how do you deal with those types of constraints in collecting your data and using it?
Okay, so basically the dataspace itself doesn't, apart from the separation of tenancy spaces and graphs, doesn't give you much. I mean, it's something that you need to design. So remember that every time you write data, you write it in a logical address. That logical address is a hierarchical address that actually you can create paths. So basically, every time I write a statement, I'm going to write that in my tenancy logical space. So there is no way I can read other tenants' data. So that's the first barrier. The second barrier is I can write that into a specific space. And what we're adding now, especially because of React Core, they did this for us. They're using role-based access control as part of React, so we're going to inherit that, and we're going to allow you to do a role-based access control in obviously in spaces and graphs. So I will be able to say this user cannot use this graph, this user cannot use, or this can access only these. The other thing that we're planning to do is use pattern matching to limit what a user can see. So, for example, if you don't want somebody to see the information about a consumer's sex or gender or religion, what you can do is that you can ban certain patterns. So, for example, what we did before is, marketeers can see the data, but they can never see the name of the person. So they can see anonymous data because there is no reason why a brand manager would like to know the names of 10 or 50 million consumers, right? So we will typically obfuscate that. So we can do that with pattern matching. We can say if there is a pattern that is trying to match this particular property, that is going to be projected out because this consumer or this brand marketer cannot cannot see that information. Now, if I'm in legal department and I need to get access to the name and address of this specific person, I might be able to do that because I have the rules, role-based access control that allows me to do that. Now, apart from that, there is nothing else in terms of, for example, regional limitations that we can impose. It's something that we can work with you to try to understand and see if we can find a solution for that. So, for example, if we have a multi-data center hosting of the data space and want to replicate between data centers, and then you want to eliminate certain data from one replica because you don't want to show that, you want to replicate to the US, but you don't want the European nationals' data to be in the US replica. We can probably come up with a solution for that.
Thank you, Alejandro. That makes perfect sense. Now, again, apologies to everyone attending. We can only accommodate 2 further questions. And the first question I would ask you is from Louise. Louise is asking, in terms of available channels that you're using to sort of reap and harvest information, would you say that Leapsight Semantic Dataspace is negatively dependent on any one of them, in a sense of any one of them disappearing, influencing your results, outcomes, the information you collect and the conclusions you come to?
No, I mean the whole idea of the data space, the whole design was all of these sources will appear and disappear. So if you ask me, I think Facebook will disappear and another Facebook will appear, or replacement will appear. I mean, even if you have children, I have 3 children, they're starting to stop using Facebook, right? And that's why Facebook's starting going after Snapchat and all these different environments, because youngsters are going out of Facebook. All these youngsters don't want to be in Facebook where their mothers and dads can actually see what they're doing. So basically, it is a very dynamic environment. So we are agnostic. So there is nothing in our design that precludes or includes Facebook as a special kind of thing. I mean, the only reason why I mentioned Facebook and Twitter is because obviously there are the major platforms out there, and in the case of Facebook, they already adopted RDF, which basically means I don't need to do any transformation of data when I bring data from Facebook. And we are kind of betting that others will follow suit and adopt RDF as well. But in terms of dependency, no, there is no dependency. In terms of, obviously, it will depend on your domain, which kind of data, and it will depend on your consumers, which kind of data is more relevant or not. For some consumer products, maybe the behavior of a consumer in Facebook is more important than what the behavior is in other social network. But we're agnostic to that.
Thank you, Alejandro. I think that that clarifies that particular issue. And finally, the last question from Dimitri. Dimitri is asking, what, if any, is the scalability limitation on the Leapsight Dataspace platform?
Oh, I mean, obviously, we are not claiming this. I mean, there are limitations as in with any technology, and obviously, in the early days, we're going to find more limitations, and we will need to work with the early adopters to work solutions for that. I would say that the first limitation is obviously because it's an in-memory technology in principle. So obviously there are limitations to what you can store in memory, and depending on the budget that you have, what you can store in memory as opposed to what you can store in disk. So that's why what we are planning to do is, or the way we want to design this to be deployed is, all the data that you will collect about the interactions of the consumer will not end up in the data space. That will go into disk. Now that might be our own solution as part of the space. So this, a space disk-based solution that you can query using the same language, using the same architecture, or you might want to do that using Hadoop or similar technology, for example, Disco in Erlang. Now, when you apply, that goes into the learning loop. Then you apply all your magic, and out of that will come out, summary facts and also new rules. And those are the things that I'm going to use to make decisions online, right? So what I want to store in the space is the data that I need, the active set that I need to be able to make decisions online, right? So the first limitation is that one. The second limitation comes to the number of indices and the way you want to operate with it. So if you want to be able to say, bring me all the information for Alejandro in all the graphs that Alejandro store in, then I need to store 6 indices, the ones I've shown, right? And that means 6 copies of the data, so more data in memory. Now, if I only going to operate by graph, let's say that I will never say, get me all the data in all the graphs for Alejandro, but I will say, give me the data for Alejandro's data from Facebook, or give me the Alejandro's data from the profile 1, or give me the Alejandro's data from the Twitter data, then I can only use between 3 and 4 indices, which obviously is cheaper to maintain in memory. And finally, some of these indices will have a bound, right? So when I store the data for a particular graph in the graph index, I'm storing all the data for that graph in one vnode, and that is in one Erlang node. So I need to be able to understand how I design, how I write my data, how I partition my data in graphs to be able to avoid an overflow of a graph of a vnode. Now, one of the ideas that we have is to be able to handle that overflow by writing into disk, but that will affect, obviously, the performance of the write and the performance of the read following that write, right? But those, I would say, are the initial limitations that we're thinking of.
Thank you, Alejandro. To close up the question session, as we've really run out of time, I'm sure that everyone will join me in thanking you for what has been a fascinating talk on the Leapsight Semantic Dataspace. Many thanks to all of you who have joined us for the webinar as well. Please join us again for our next monthly webinar, and following today we will be sending you a short survey just to make sure we capture your feedback of today's webinar. Please also note that the recording of the webinar and the presentation that was shared today will also become available for you to collect on our Erlang Solutions corporate website at erlang-solutions.com. Thank you all once again. Please send us any further questions you might have, and we look forward to seeing you on our next webinar.